Great. So the title of my talk today is Programmable Interactions and Emergent Geometry in an Array of Atomic Ensembles. It's about some work that we're doing in my lab on advancing control over interactions in systems of laser-cooled atoms. And I don't think I need to convince you, particularly after Jörg's talk, that cold atoms are wonderful tools for studies of quantum many-body physics. With some of the kind of recent developments are astounding levels of single particle control and single particle detection, but also these are systems where there can be well-controlled interactions, and I've shown kind of a couple of examples here of various systems where one, for example, sees antiferromagnetic ordering either of fermions in an optical lattice due to their contact interaction, or in this case of some spins that are encoded in Rydberg atoms with long-range van der Waals interactions. So these are some of the tools that are available to us in systems of cold atoms. But one of the kind of limitations that most experiments in this field face has to do with actually the connectivity of interactions. And so in these examples I've shown you, where we see this antiferromagnetic ordering, it's coming about from some local interactions where, interactions between nearest neighbors dominate. And there are a number of reasons why you might want to be able to go beyond building systems where interactions are constrained to be local. One way you can see that in the sort of classical world is, isn't it amazing in this era of Zoom that we can talk to each other irrespective of the fact irrespective of physical location, right? So we know that connectivity governs the flow of information, and the fact that the internet gives us non-local connectivity really changes the way that, let's say, scientific collaborations form. So in the quantum world, similarly, the connectivity of interactions governs, for example, the types of quantum state, many-body states that one can realize. So if I had, for example, Ising interactions between nearest neighbors on a lattice, that's a natural way of dynamically generating a cluster state, which is a resource for computation. But if I have the same form of interaction and every atom talks to every other, that could generate a squeeze state that's a resource for enhanced precision measurements. If I have some random graph of interactions, that might be a way to explore the phenomenon of fast scrambling of quantum information, where locally encoded information very quickly becomes hidden in complex correlations among many degrees of freedom. And that, in turn, could be a toy model for what happens to information in a black hole. Or if I have sufficient programmability of the interactions between the constituents of my system, for example, I could take some classical computational problem and map that to the problem of minimizing the energy of my quantum system. But that requires some programmability of the couplings. So the sort of vision that we have in my lab is having versatile control over the graph of interactions in a quantum system. And just to give a little bit more motivation, building on sort of the theme of quantum dynamics, that's of interest to many of you, I think, let me sort of zoom in on this example of what would it take to realize a fast scrambler of quantum information. And for us, this was actually kind of a motivation for some of the experimental developments I'll talk about today. So say I want to study kind of fundamental limits in quantum dynamics. A fundamental limit to how fast information can spread from 1 to many degrees of freedom is, it was sort of pointed out, coming from the study of what happens to information that falls into a black hole, that there's a fundamental bound on how fast information can be scrambled or delocalized across the system. And that fundamental limit involves an exponential spreading of information from 1 to many. Which wouldn't happen in sort of a system with local interactions, but does happen in some toy models that one can write down on paper, such as this SYK model with all-to-all random couplings. Or also actually some sort of early toy models for fast scrambling involved systems of billiards on tree graphs, for example. So here interactions are local, but in some very exotic geometry. Okay. So if you'd like to start to explore some of these things in the lab, let me kind of draw some inspiration from the example on the left. We won't realize precisely this SYK model, but we can sort of do some things that are similar in flavor, in the spirit of sort of having the ability to have particles that can hop non-locally. In our system, the particles are spin excitations, And in order to get them to sort of hop over long distances, the hopping process is mediated by light. So we have a physical system where we can, if I sort of think of a spin excitation as a particle on a site, then if I can make a spin exchange interaction that is non-local, that would correspond to this sort of non-local hopping. The way that we do that conceptually, here's kind of a simple example. If I have two-level atoms, and I want to generate some non-local spin exchange interaction, what I can do is I can convert an excitation in this atom on the left into a photon, right? If the atom can flip its spin and emit a photon, and if that photon is absorbed by another atom, that allows me to have this spin exchange interaction that is sort of as long-ranged as the mode of the light that mediates the interaction is spatially delocalized. And so this gives a way of giving sort of effectively non-local interactions over some volume within an optical resonator where there is strong atom-light interaction. In our we in the lab we have essentially an optical resonator. It's really just two mirrors 5 centimeters apart that allows us to have strong atom-light interactions. And within that resonator, we trap an array of, in our case, little clouds of atoms. So these aren't individual atoms, but we have an array of about typically 20 sites, each with some thousands of atoms. And the idea is that photons should be able to mediate interactions between arbitrary atom pairs in this system. And we'd like to also get to the point where we have some programmability of the structure of those interactions. So before I kind of show you data, I'll tell you a little bit more about the atoms in our system. In our system, each atom has, actually, I sort of gave the spin half example earlier, but each atom actually has a spin 1. So it has these 3 magnetic sublevels, -1, 0, and +1. And one of the ways that we like to probe the system involves initiating the atoms in the 0 state. And in that case, in the simple case of 2 atoms, the process that you would expect to see is one where if you send in a control laser, a photon can be scattered by the first atom, which flips its spin from 0 to the -1 state, and the second atom rescatters that photon and gets converted to the +1 state. So I drew it here in kind of an asymmetric way, but really you should think of this as a way of taking 2 0 atoms and making this superposition of one atom being in the -1 state and the other in the +1 state. Okay, so that's the basic mechanism that we're going to use to kind of probe the interactions and the dynamics in this system with non-local photon-mediated interactions. And we won't look at 2 atoms. We'll look at this system of many little clouds of atoms. And the first thing that you can do to kind of sort of see these atoms interacting is start with all atoms in the 0 state, turn on some light that should turn on the interactions, and then measure after some fixed time the populations in these 3 internal states. And so what I'm showing here are some pictures where each row is just a different iteration of exactly the same experiment. So this is 30 repetitions of the same experiment. There's in each column I have actually sort of position in this array is the horizontal axis. And we have the populations for these 3 internal states that we image independently. And what you'll see is that from shot to shot, you'll see some large fluctuations in the populations, but you'll sort of notice those fluctuations are correlated, right? So some shots we have more atoms in the -1 state and also in the +1 state. And this is starting to be a signature of this process of the light-mediated interaction that generates these correlated atom pairs in the +1 and -1 states. Okay. So far, one thing you'll notice is there don't seem to be any interesting spatial correlations. More or less, if there are more atoms in the -1 state, you see that kind of uniformly across the atomic cloud, across the array of atomic clouds. So this is kind of showing all-to-all interactions mediated by the light. And we would like, I said, to have also some control over the structure of these non-local interactions. And in particular, the dream might be to have arbitrary control over the connectivity. Will be slightly more modest and say, can we start to have control over any translationally invariant form of interaction? So our goal will be to have sort of any dependence that we want of the structure of interactions as a function of distance in the array. Okay, so how might we do that? So the first thing that we do in order to have this control is actually to break down the all-to-all connectivity by applying a magnetic field gradient. So ordinarily, every atom could talk to any other, but if we apply a magnetic field gradient across this system, then we have a scenario where the process of creating a +1 -1 pair is only resonant for two atoms that are sitting on the same site. If the atoms are some distance apart, right, then that process does not conserve energy in the magnetic field gradient. And correspondingly, if we do the same experiment, start with all atoms in the 0 state, turn on the interactions, and measure at some fixed time, what I'm showing you here are basically spatial correlations between population in the +1 state on site I and population in the -1 state on site J. And you can see the correlations are strong on the diagonal, indicating that these interactions are local and are giving rise to just these short-range correlations on each site. Okay, so now, though, we can take this one step further. So I showed you we can get all-to-all connectivity, we can get local interactions. And now it turns out that if we want to, say, turn on interactions at some particular distance, all that we need to do is drive our resonator with two laser frequencies. That allows the atoms to, an atom to absorb a photon of one energy and another atom to emit a photon of another energy. And that gives a way of sort of bridging the cost of creating a +1 -1 pair at some distance. Okay, and so here you see these correlations appearing off the diagonal. In this case, showing that we've turned on interactions at a distance of 10 sites in addition to the local interaction. Okay, and that you can vary. So essentially what we're doing is really intensity modulating the laser field so that there are these two frequencies present. And as a function of the modulation frequency, if we look at spatial correlations, so horizontal axis here is basically showing correlations versus distance. Vertically, we're varying the modulation frequency. And you can see that the distance at which the correlations are strong tracks the modulation frequency. So that's showing programmability of the interaction distance, and we have very fine control. We can really see discrete peaks for interactions at 10 sites, 11 sites, 12 sites. And now you can imagine generalizing this. It's actually quite easy in the lab to control the spectrum of the laser field, and that should allow us to control, in an essentially arbitrary way, the interactions as a function of distance. Okay, so to give a little bit more of a picture for sort of how I like to think about this, I sort of gave a picture in real space where the frequency separation between sort of two teeth of my drive field sets the distance at which the interactions are on. It's also kind of nice as a complementary picture to think about this in momentum space. So if I take a Fourier transform, I can conclude that actually the waveform in time of my laser field actually sets the energy as a function of momentum. So it sets the dispersion relation for spin excitations in this system. So that's another way I can think of this. Writing my Hamiltonian momentum space, this energy versus momentum is set by the temporal waveform of the drive field. In our system, actually, and there's a minus sign in front, so minimum intensity corresponds to maximum energy. In this particular system of this spin 1 physics, it turns out that the peaks in, the energy minima are also maximally unstable to creating these correlated atom pairs. And so one of the things that we can see actually is if we analyze the time evolution or plot the time evolution, we can look at it in real space or in momentum space. In real space as a function of time, if in this case I turn on interactions at a distance of 3 sites, I'll see correlations sort of spreading from to a distance of 3 sites, 6 sites, 9 sites as a function of time. Or equivalently in momentum space, I can think of this as some peaks appearing in the structure factor at a momentum that corresponds actually to a peak in my modulation waveform. And this is really coming about from the fact that the modulation waveform sets the dispersion relation, and the energy minima are maximally unstable to creating these correlated atom pairs. Okay, so that's the time evolution. And it sort of corroborates this picture that I can engineer the dispersion relation with the modulation waveform of the drive field. One kind of interesting subtlety that was actually pointed out by one of my students is that, well, this is a finite size system. So really, if I'm thinking about sort of engineering the dispersion relation, this should only be defined at discrete points in momentum space. So if you take that literally, you would say maybe I shouldn't be driving continually my laser. Maybe I should actually be pulsing it on at discrete times. And it turns out if you do that, you precisely realize the dispersion relation for the finite size system with periodic boundary conditions. So that shows up in this plot of correlations versus modulation frequency as saying that, for example, if we have interactions at a distance of 2 sites, we also have interactions at a distance of the length of the chain minus 2 sites. So that's kind of a neat knob that we have. You can have open boundary conditions, or you can engineer periodic boundary conditions, even though physically the system is just a linear chain. So that starts to show you that the geometry of the interaction graph doesn't have to be the same as the physical geometry in our system. And one of the things that we like to do to kind of actually directly from the data see what is the actual geometry of the graph that we've engineered, we can actually directly go from sort of the measured spin correlations to ask, we think we've engineered, let's say, this ring with periodic boundary conditions. Do the data agree? And so we can, for example, take these measured correlations and say, what is the best sort of geometrical representation of the different array sites to explain the measured correlations if we adopt some ansatz that correlations decay with distance in some effective geometry, right? So we're going to try to find some effective coordinates that explain these measured correlations. In our case, it's natural to adopt a Gaussian ansatz. And if we do that, what we find in this case of nearest neighbor interactions and periodic boundary conditions is that, in fact, the sort of reconstructed geometry by this black box technique straight from the experimental data looks a lot like a ring. And here we've actually drawn all possible bonds, and their opacity is set by the correlations, specifically extracted from the inverse correlation matrix. And so it really, what pops out is the ring. And OK, so that kind of corroborates that we have that graph. And now you can kind of play with different waveforms and see what geometry pops out. And just as a few examples, you can make this ring, but you can also make a Mobius strip. You can make an a ladder geometry, a cylinder. And these are just by different sort of coupling graphs that we program in with the spectrum of the drive field. And one other thing I'll highlight here is the color of the bond indicates the sign of the correlations. And just by sort of a phase that's either 0 or pi in the modulation waveform, we can control are the interactions and the resulting correlations ferromagnetic or anti-ferromagnetic. So those are all tools that we have, and there are kind of a number of different directions that one can take these. One thing I highlighted here, for example, are the ability to have anti-ferromagnetic interactions that are of interest for studying frustration, for example, realizing potentially frustrated classical XY models and asking whether the quantum system can help to find the ground state. Sign-changing interactions could be interesting for studying spin glass physics. Some of the graphs I've shown you can realize in other ways with local interactions. So we're particularly interested in kind of what are the unique things you can do with these exotic non-local interactions. And that brings me back to this sort of topic I mentioned earlier of can one realize some kind of toy models for phenomena such as fast scrambling or models inspired by quantum gravity. So in that vein, for quite a while, actually, before realizing this level of control in the lab, we have been dreaming about what are some of the things one might be able to do with it. And we've been thinking about sort of what would it take to observe exponentially fast spreading of information across a quantum system. And one sort of toy model that in principle ought to allow that in this system is one where you have couplings. So in our system, the couplings will be translationally invariant. But imagine that you have couplings that are at distances that are powers of 2. So 1, 2, 4, and 8 sites in a chain of 16. That sort of should give an efficient way for sort of any site to talk to every other in a number of steps that's logarithmic in the system size. So we had kind of been thinking about this toy model. You can add one more ingredient, which is some power law exponent that decides do the interactions decay with distance or do they grow with distance. And if they decay with distance, the coupling graph looks like what I've shown on the left. It's not that different from a linear spin chain. If they grow with distance, then that looks a bit more exotic, right? The strongest bonds are between furthest neighbors. You can kind of actually rearrange the ordering of the sites compared to the physical order, so it starts to look a bit more local. And I'll try and convince you actually the right way to think of this system is that the sites are arranged on some sort of a tree graph. Okay, and the conjecture is that actually at some point in between these two geometries, everything is kind of strongly connected to everything else, and this should be a fast scrambler. What we've focused on so far is actually the sort of right side of this slide. Can you realize this weird tree-like geometry? And so, we can just program in that structure of interactions. They're at distances that are powers of 2, and they grow with distance. If you measure the correlations in the system, they have some rather exotic-looking sort of non-monotonic dependence on distance. This starts to look a little bit more structured if you reorganize the sites in this analysis. So I plot these same correlations, but I reorganize the sites according to their position on that tree graph. And then you'll start to see kind of a hierarchical structure in the plot of the correlations. There are some blocks that start to appear. And if you ask actually what are the correlations as a function of sort of the natural measure of distance in the tree, which has to do with sort of how many steps up the tree you need to go to connect two sites, then you actually see a smooth decay of correlations versus distance in this sort of exotic new geometry. We are kind of intrigued by this because this tree graph is actually considered is a sort of a toy model for the idea of holographic duality, where I have some physical system that lives on the boundary of a higher dimensional space that encodes something about the structure of correlations in the physical system on the boundary. So this is this idea that there's sort of one extra dimension with curvature that might come about from gravity that gives a notion of distance that's related to the correlations in the system on the boundary. So in this particular case, in contrast to other graphs I showed you where we really engineered, let's say, a Mobius strip, here the tree isn't physical, but the tree is supposed to capture something about the structure of the correlations in the quantum system. So if you want to sort of really directly check that, is this tree graph a good description of the system, we can sort of adopt the procedure I showed before, where we first ask, what is sort of a good geometric picture for thinking about the positions of the sites in some effective geometry where correlations decay with distance? I'm doing this here actually for two cases. One is the one where interactions decay with distance, and it's not too different from a linear chain. This is the case where interactions grow with distance, the sort of more exotic regime. So the first thing is we reconstruct sort of the site positions in 2D, some effective positions that explain the correlations. And then we adopt a coarse graining procedure where we draw bonds between sort of the most strongly correlated sites. So we measure correlations between the spin on site I and site J. We draw bonds between the most strongly correlated sites. We treat those as a larger site and repeat the process until everything is connected. And if you had the sort of interactions that decay with distance, this kind of looks trivial. You end up with this ring. But if the interactions are in this model that grow with distance, you actually see this tree graph emerge from this kind of coarse graining procedure. So that is kind of a neat toy model for this idea of a holographic bulk geometry. But the other thing that you can ask is now we have these two kind of radically different geometries that you can tune between with a single parameter that's this power law exponent. And if you do that, so here we're actually varying that exponent s and asking how strong is the correlation between kind of two halves of the system if we cut the system in half. So for example, if you have the s is less than 0, so interactions decay with distance, and you cut the system according to the physical geometry, then the correlations between the two halves are relatively weak. And similarly, if s is greater than 1, I should cut according to the tree graph in order for the correlations between the two sites to be weak. That's shown in the two sides to be weak. That's shown in green. But if actually I go in between, I set this exponent to 0, so interactions are sort of strong on all length scales, there's actually no way to cut the system so that the two halves are weakly correlated. And that is potentially sort of the right starting point to be able to explore perhaps fast scrambling in the lab. Okay, so with that, I will just kind of conclude and say that I've shown you a pretty versatile toolbox for programming interactions. In the system of cold atoms, we can control the graph of interactions, the sign of interactions. We have a way of reconstructing some effective geometrical description of the system directly from experimental data. This would be nice to take these tools and go deeper into exploring the dynamics. How do the dynamics depend on the interaction graph? Are there situations where this kind of picture of a holographic bulk geometry gives some insight into, or a nice way of thinking about the transport in the system? And lastly, also, we're interested in kind of exploring applications of these programmable graphs to problems in optimization or generating new spatially structured entangled states. So with that, I will just kind of thank the team of people who made all of this happen, and I will take any questions.
Okay, thank you very much. So, Nicole, you have a question.
Sorry, I was on mute. Thanks for the very, very fascinating talk. It's amazing to see what you've realized in the lab. I was wondering about the ring structure that you showed. It seemed to have one non-uniformity, one sort of deformation. And I was wondering, is that just some artifact that isn't very important? I was just wondering why it isn't homogeneous.
That's a great question. And it is an experiment, and experiments usually aren't perfect. What is the limitation in this case? In this case, the defect actually is between the two ends of the chain in the physical geometry. And I believe that is from some combination of the atom density being a little bit lower at the edges of the system and the intensity of the cavity mode also being a bit weaker at the edges. And in principle, there are ways to compensate that. So there is a bit of a defect. On the other hand, actually, in the case I showed towards the end with this, the model where I was showing the bulk geometry for the tree, the reconstruction of the opposite limit, where it was more like a linear chain, actually looked almost perfect. So, and that was a different data set and a slightly different interaction structure. So, I think to me I think in this case it may be related to this inhomogeneity at the edges of the system, but I would say it's probably not fundamental and could be addressed. So, yeah.
Okay, thank you.
Mm-hmm.
Jörg?
Hi, Monika. Fantastic experiments. I have one question. So why do you use the ensembles instead of single atoms? Because on one advantage of the ensembles would be that you can, look at full distribution functions and see the statistics in addition to just, label it either be 1 or 0 or -1.
Yeah. So why do we use? So first of all, the sort of main reason actually why we use the ensembles is that we do benefit from a collective enhancement in the atom-light coupling. So we're in the strong coupling regime for single atoms, but sort of barely. So we win a collective enhancement. And I think there's a kind of interesting direction of pushing towards, really maximizing the single atom coupling and going to single atoms in the cavity. But right now, I would say as you say, there's a lot of rich physics already with the ensembles. And you're right, actually, we could look more closely at the full statistics, right? There's probably a lot of information there. We're interested in, I haven't proved entanglement with the data I showed you, but that's something we're currently kind of working on in the lab, is measuring entanglement and also asking sort of what can you do when you can program the spatial structure of correlations between these ensembles. And so actually, it's maybe worth mentioning in terms of kind of the outlook, ultimately for some of these things like, studying fast scrambling. This would be most interesting in the regime where it's really kind of a single quantum spin on each site, in the sense that that's sort of the regime where you really can't calculate it and have to do the experiment. For us, for this sort of early time dynamics with many on the site, some semi-classical methods work quite well for modeling the experiment. So it's in a regime where we expect to be generating entanglement, but still in a form that is kind of amenable to some numerical simulations. But again, for some directions, like this question of can you use the system to solve some optimization problem, that would already be really interesting to study actually in this system of ensembles where there seems to be some kind of the dynamics naturally give rise to actually kind of low energy states of the classical spin model. So yeah, and so I think there are really interesting directions in both regimes.
So one quick question. So did you look at also higher order correlations and factorization and things like this?
We haven't looked at higher order correlations that,
they could give you really details about the interactions and their quantum corrections, you know?
Yes, yeah. So I think this is something that would be great for us to think about in the future. Yeah, yeah. And maybe this is something we should learn from you about. So yeah, it's a great question.
Anytime, you know?
Yeah.
Anytime.
Yeah. Mm-hmm.
Okay, Tarun?
You can share all the programs you want, you know, if you want them.
Great. Yeah, very nice talk. Thank you for this. I just had maybe two very quick questions. So did you try creating a two-dimensional lattice with local interactions by choosing your long-range interactions in a way so that it mimics that, or is that too hard? Because it won't be then it won't have this form. It won't be like only a function of I minus j. If you want to create 2D local systems by starting with your.
Yeah. So actually, let me see whether I have one slightly different slide. I have to, sorry, I just want to actually show a different slide if I can, but I have to stop the share and restart it. I think it will help answer your question.
While you're looking at it, I mean, I can maybe just.
Okay, I'm not sorry. I will. I'm just going to say it in words.
Sure. Yeah.
So basically, like in these examples, you can see this again, right? The gallery of graphs. So these things like the Möbius strip and the cylinder are essentially like 2D systems plus periodic boundary conditions. I mean, in this case, the second dimension is pretty short. But the way that we do it, like the Möbius strip, for example, the way that we actually make it is we have 18 sites and we have nearest neighbor interactions and we have interactions between ninth neighbors.
Right.
So that's an example of precisely that type of scheme.
So, but how large can you make can you do like, I don't know, 10 by 10, 20 by 20 2D lattices? Or
oh, yeah. And so for us, I think in terms of kind of limitations on how many ensembles we can fit into the cavity, it's probably hard to go above like order 100 in terms of the total number of sites I would say, in our existing scheme. And I think it's probably an interesting question to ask. If you really push things, how far can you scale it? Can you use a second dimension physically to also pack in kind of more ensembles spatially? So I think there are directions to scaling that up more, but I would say 100 is about what's natural in our current system.
Yeah, I was wondering whether are there, for example, something like the Kitaev honeycomb model or anything more exotic, which has, I mean, okay, that's maybe, yeah.
Maybe I would say that actually, in my opinion, in some sense, for these local lattice models, it's not clear to me that this is really the best way to do it.
I see.
I think there are systems with, let's say, Rydberg atoms that are really naturally suited to studying like spin models with local interactions. And so for me, the strength of this system is more the ability to go beyond that and have this really versatile control.
Right. No, I agree with that. Yeah.
Okay. Johannes?
Hey. Yes, again, also thank you very much. Very cool experiment. Very nice talk. So the one thing I just wondered about, because you talked about full controllability and you want to use it for, say, combinatorial optimization. So how are you going to prepare low energy states in the system? Because at the moment, I think it's more like you want to prepare driven dissipative states. Which are
this is a really great question. So
but how do you get to low?
Yes, and I kind of glossed over this. So you can start to see, so I kind of hinted at this a little bit when I said what the physics of this pair creation is basically something where if I can think in sort of momentum space, there's kind of an amplification of certain momentum modes that are correspond to the minima of the dispersion relation. But kind of another way to think about this that, because it's not at all obvious, right? I suddenly turn on interactions, why should I generate a low energy state? So what's kind of going on here is we have these three internal states, and there's a quadratic Zeeman shift, which means that creating a +1 -1 pair actually has a small energy cost in terms of the internal state energy. And that actually allows the system to lower its interaction energy by increasing this quadratic Zeeman energy. And so, for example, like when we engineer, one of the graphs we engineered is this anti-ferromagnetic ladder. We just really, again, it's just dynamics. But what happens is that we do, in fact, see anti-ferromagnetic correlations and that actually match very well to what you would expect, which is a roughly sort of 120-degree ordering on this lattice. So you can see that if you look at sort of correlations versus distance, or also if one looks at kind of the structure factor, there are sort of peaks that correspond to the phase of these spins winding by sort of 120 degrees per site as I sort of go along this ladder. So that's a really kind of neat, almost unexpected thing about this system is it does lower the energy of sort of the XY interaction by increasing this quadratic Zeeman energy. Yeah.
Okay. Mohammed. Yes.
Hi, thanks for the nice talk. Actually, my question is maybe related to the previous question, but not exactly. Can you make the Hamiltonian chiral in the sense that you would have flip-flop, but not flop-flip interaction?
I think so. Let me make sure that I'm thinking of the right thing. So one of the things that we can do is actually, and it's related actually to this quadratic Zeeman energy. So it turns out that we work in a regime where this quadratic Zeeman shift is relatively small compared to the interaction energy. But in general, actually even on this plot, it's not entirely negligible. And what you'll see is there's a slight shift of this peak that ideally is at 0. It's slightly shifted. You can see a little bit of a sort of side feature on the right. And that actually has to do with the fact that if you sort of take this to a case where there's a stronger quadratic Zeeman shift, you could actually engineer something where you can create like +1 on a given site and -1 on the site to the left, let's say. Like that, you can make that be the resonant process. And I think that's related.
I see. So that's actually going to be non-Hermitian, but that's okay, right?
Yeah. Okay. So is it also chiral or no?
It's, yeah. I mean, I guess it transports particles one way, so it's chiral, but also it's non-Hermitian.
Yeah.
It's kind of like this asymmetric exclusion processes or something like that. So,
yes.
But, okay.
Yeah, I think so.
In principle, that's the message I'm getting. In principle, that's possible.
Yeah. And then the other thing you can do that might be related is you can control the phases of the couplings, right? So we can put in any phase we want of the couplings as well.
Cool.
So,
thanks.
Yeah. Mm-hmm.
Thank you. Philippe.
Hi.
Hi.
Thanks for the nice talk. I have one question I have is at no point you consider dissipation, right? So I'm wondering if the sort of the finite cavity line width, you really don't care about it because your cooperativity is large enough, or is it something that at some point I should worry about?
Yeah, so definitely at some point you should worry about it, and this is in some sense kind of related to your question, like why do we work with many atoms? For us, we do benefit from having a large collective cooperativity on each site. And so for the collective dynamics, the dissipation, it's not negligible. Sort of at longer times, there are sort of two processes that can hurt. One is instead of having these flip-flops, you could have just a sort of single spin flip and the photon leaves the cavity. And then there's also free space scattering that can redistribute atoms between different internal states. And so neither of those is negligible. We do sort of, at our longest experimental times, there is some substantial fraction of the atoms actually have scattered a photon. So, and these collective dynamics are relatively robust to that. And so it's sort of right now at the level where, for example, if you want to ask sort of how quantum is the system, we would expect, based on our parameters, to be able to measure squeezing, for example, as a measure of entanglement by sort of, for each individual ensemble, if you sort of turn on this gradient, you could have, like, you know, this array of ensembles, and each of them has 10 dB of squeezing, for example. Or you could control with the spatial structure of the interactions, you know, the entanglement in some other structure of the collective modes. But so, yeah, so it's in a regime where it is ultimately a limitation if you want to study long-time dynamics or get to like very non-Gaussian states, for example. There, potentially, I think that would be a limitation. So, yeah.
Thanks.
Mm-hmm.
Any other question? Okay, so let's thank everybody, and we'll reconvene tomorrow.